Cosmic rays are highly energetic particles that move through space at relativistic speeds and arrive in the Earth's atmosphere from outer space. They're one of our few direct samples of matter that come from outside our solar system. Cosmic rays are composed of 89% hydrogen nuclei, these are protons, 9% helium nuclei, these are alpha particles, 1% heavier nuclei, 1% electrons and gamma rays. It can be said from this that cosmic rays are charged particles. Some of our cosmic rays come from the Sun. These rays have relatively low energy. However, this is only a really small portion of cosmic rays. It's unlikely that a randomly chosen cosmic ray will have come from the Sun. Other cosmic rays originate from the Milky Way galaxy beyond our solar system. Cosmic rays are more likely to come from outside our solar system than from our Sun. Such rays have medium to high energy. The remaining cosmic rays come from other galaxies outside of our own. These are extragalactic cosmic rays, and they have the highest energy, approximately 10 to the 18 electron volts. The highest energy cosmic ray ever recorded, the OMG particle, had an energy of 3 times 10 to the 20 electron volts. And this came from outside of our Milky Way. Cosmic rays can be detected at the ground level by using large tanks of water scattered over a large area. An example of this is the Pierre Auger Observatory. The cosmic ray particles travel faster than light in water. This results in the surrounding molecules emitting blue light called Cherenkov radiation. This light is detected by photomultipliers in the tank. Atmospheric fluorescence can also be used to detect cosmic rays. Cosmic rays close to atoms in the atmosphere excite the electrons to higher energy levels. When electrons return back to lower energy levels, a photon of light can be detected. Cosmic rays are charged. When they're emitted from their origins, as we discussed earlier, their charge allows them to be deflected across various magnetic fields. On the journey to Earth, the magnetic fields of the galaxy, the solar system, and the Earth scrambles their flight paths so much that we can't directly calculate where it came from. Regular light can be easily traced because it travels in a straight line, as shown by the purple line. You can see the effect of the magnetic fields on the cosmic ray, however, which causes a scrambled path. Thus, we can only use indirect means to calculate the origin of the cosmic ray. A cosmic air shower is an extensive cascade, often over many kilometers, of elementary particles and atomic nuclei, all stemming from a primary cosmic ray coming into contact with the Earth's atmosphere. Cosmic rays can consist of multiple particles, with the main one being protons, as we discussed earlier. However, they could also consist of electrons, photons, or even a positron. The atomic nuclei found within cosmic rays can range all the way up to uranium and can be as heavy as nickel. However, heavier nuclei are more uncommon. When one of these particles from the primary wave come into contact with the nuclei within air particles, it can produce high energy hadrons, for example, pions, kaons, and baryons. These hadrons created from the first interaction are highly unstable and therefore quickly go on to decay to produce further particles and electromagnetic radiation. For example, a neutral pion decays into photons and gamma rays. A charged pion also decays, however, they take longer to do so, which can result in the pion coming into further contact with other particles in the air, consequently forming muons, and neutrinos, amongst other things. These particles and this radiation can be classified as the secondary wave and include X-rays, muons, protons, antiprotons, alpha particles, pions, electrons, positrons, and neutrons. Although some ultra-high energy particles have the ability to reach the Earth's surface, most particles do not and cascade to form the shower. It is then by studying the shower of cascaded particles that we can determine the origin and the original composition of particles within the cosmic ray, which came into contact with the Earth's atmosphere.
The sun has fascinated generations and generations of mankind. Yet only recently we have fully understood the grandeur and scale of such a beautiful object that light in the sky. It has provided us with life for millennia, and, well, not us specifically, but other organisms with life for millennia. And, to truly appreciate the structure of it, we have to look at the layers. The layers of the sun range in depth, texture, and purpose. The outermost layer could be considered as incredibly far-reaching, although it is usually classified as just the corona. Solar wind, however, is of the same composition, ionized gas, which reaches much further from the surface of the sun, as we'll learn about later from Connor. Although it cannot be seen on a regular day, when an eclipse occurs, the majority of light emitted from the sun comes from the corona, and hence why it can be seen so clearly in this picture. It is comprised of plasma, hot ionized gas, and it has a temperature of approximately 2 million Kelvin and a density of about 1,000th of that of the atmosphere of the Earth. The next layer is the chromosphere, and in this image it can be seen as the red furrows that peek out from behind the moon. This layer is the lowest layer of the sun's atmosphere, only a few thousand kilometers thick. The temperature in this zone varies from 4,500 to 100,000 Kelvin. This again is sort of loosely defined, as it is effectively pretty homogeneous columns of cooler gas surrounded by more corona-esque hotter gas between them. These layers end up merging together as the distance from the core increases and it becomes the corona. The reason we see it as red is because at these high temperatures, the hydrogen emits a red light, and this phenomenon is known as H-alpha emission. Here, the radiation can be seen through a lens isolating the light released from H-alpha emission. This emission is specifically from electrons moving between the second and third orbits. After this is the layer that we all commonly recognize as the surface of the sun, as it is the one that we see from Earth, and it is appropriately named the photosphere, as pictured here. Although we consider this to be the surface of the sun, as it is the one that we see, since the temperature is so great, and because of the chemical composition of the sun, it is only a gas, so it isn't like the same surface that we have on Earth, but only where the gas becomes less opaque. This, alongside the chromosphere, is the only layer of the sun cool enough to house hydrogen in its atomic form, and the same sort of electron excitement happens in this layer. Although what we see is more of an absorption spectrum, since the gases get cooler and cooler further from the center, and therefore have less electrons jumping around, and are more likely to collide with a photon that is trying to escape. From this spectrum, we can infer things like the chemical makeup of the sun, and thus its age, and many other interesting facts. The interior of the sun can be split up into three regions: the convective zone, the radiative zone, and the core. The outermost of these is the convective zone, as seen here. This has a depth of about 200,000 kilometers and ranges from that depth in the sun to the photosphere. And like the rest of the core is made up of plasma. And just like the chaotic conductive patterns that arise when boiling water, convection occurs within the sun as well. And the source of heat, instead of a gas stove, in this case is the radiative zone. And the energy that is released from this will heat up the water, and instead of creating bubbles, it will create solar cells, which act in a very similar way. Beneath this is the radiative zone, a zone through which the energy created from nuclear fusion in the core moves outwards in the form of electromagnetic radiation. As seen in this unfortunately low-resolution diagram, this means that the energy is conveyed by photons. Since the core and radiative areas have a differing spin from the convective zone, there is a boundary that emerges called the Tackock line. This difference of rotation arises because of the convection zone's tendency to spin faster at the solar equator than at the poles, whilst the core and radiative zones have equal spin regardless of latitude. Now to the heart of the sun, the core. Within the core, energy is released by using hydrogen atoms to form helium. Of course, these are disassociated, like in the radiative zone. These reactions end up being responsible for the light that's eventually emitted by the sun, and through means that I've hopefully explained. These particles must overcome the electrostatic repulsion, and since the temperature is about 15 million Kelvin within the core, the probability of this happening is relatively high. And since the binding energy of helium nuclei is greater than that of both hydrogen nuclei and of the helium isotope nuclei, energy is released at each stage in this process. This energy is released into the radiative zone in the form of photons, which then encourages the creation of solar cells, which then carry the energy to the surface, ultimately to be released as photons from the photosphere, or as the heat that keeps us all alive. To conclude, here is a brief recap of the structure. The corona is the outer atmosphere, made of plasma and is much hotter than the layers below, other than the core, of course. The photosphere and chromosphere both emit light via electrons changing energy levels. The convective zone forms the solar cells that rise to the surface like bubbles to the surface of boiling water. The radiative zone carries the energy from the core via photons. And finally, the core performs fusion to convert hydrogen into helium to provide the energy for the whole star.
In order to understand the solar winds, we must first explore the magnetic fields within and around the Sun. It is widely believed that the Sun's magnetic field is generated by electrical currents acting as a magnetic dynamo inside the Sun. These electrical currents are generated by the flow of hot, ionized gases in the Sun's convection zone called plasma. Plasma is a heated gas of charged particles, mostly protons, electrons, and helium. These magnetic fields have many effects on the Earth and solar system as a whole. The Sun's magnetic field is so strong and extends so wide that it can protect the whole solar system from cosmic rays. For example, charged particles from space are deflected towards the Sun. The magnetic field also has some side effects on the Sun. For example, the Sun is hotter at its magnetic poles due to a larger concentration of ionized particles fusing. This difference can cause the poles to be up to 100 Kelvin warmer. This effect is also the basis behind sunspots. Sunspots are a magnetic phenomena caused by disturbances in the magnetic field of the Sun. These disturbances can cause ions to be deflected away from a spot, meaning no fusion can occur and the temperature will sink. These sunspots happen every 11 years during solar maximum and can last 11 years until the magnetic poles of the Sun switch again. These disturbances in the magnetic field are also the cause of other various solar phenomena, such as solar flares, coronal mass ejections, and solar winds. The solar wind is a stream of plasma constantly emitted by the corona of the Sun, mostly made up of ionized hydrogen. About 1 million tons of matter is released from the Sun in this way per second. Over sunspots, the solar wind has a much higher velocity, up to 800 kilometers per second. This is because the density and temperature are much lower and the magnetic field is much weaker. Around the equator of the Sun, known as the coronal streamer belt, the solar winds are much slower, around 300 kilometers per second. Coronal mass ejections, or in layman's terms, solar storms, are significant releases of plasma from the solar corona. Coronal mass ejections often follow solar flares and are normally present during solar prominence eruptions. Solar flares are explosions of energy caused by tangling, crossing, or reorganizing of magnetic field lines near sunspots. These release a burst of high-energy cosmic rays. These contain enough energy to wipe out life on Earth if not for the Earth's magnetosphere.
So as we can see, the Sun has many, many layers, each of which has a vital role in providing the heat that we get to live on. You know, the sun's power reaches much further than just the corona and into solar winds and magnetic influence on the entire, gravitational influence on the entire solar system.
So you're probably wondering, what is the magnetosphere? And firstly, in the Earth there's a molten iron core, and as the Earth spins, there's a magnetic field generated by this spinning, well, this metal turning and the motion of the metal, and we call this the magnetosphere. And I would like you to study the diagram for a bit and really look closely, because it relates to the next part of the slide. So the Earth's magnetosphere has a really important role to play, because essentially it protects the Earth against solar winds. So as you saw in the diagram before, the way it works is like putting a rock in the river. It deflects the flow of water, and in the same way, this magnetosphere blocks the solar wind attacking the atmosphere. I would like to add that examples of planets that no longer have a magnetosphere are Mars, and therefore they have no atmosphere and therefore cannot host life. So we should be quite grateful that we do have a magnetosphere. One last thing I would like to add is that the magnetosphere almost resembles that of a bar magnet, and it's tipped at 11 degrees to the Earth's rotational axis. So the next important part is talking about magnetic mirrors and bottles. So when high energy particles from the solar wind do manage to get into the magnetosphere, and when they do between the angle 0 and 90 degrees, they will change direction and spiral along the Earth's magnetic field lines and form the inner and outer Van Allen belts. And these are concentric toroidal magnetic bottles, toroidal meaning donut shaped essentially, and these have mirror points at Earth's magnetic poles, and particles tend to oscillate back and forth between these poles with periods of between 0.1 and 3 seconds. So yeah, that is really quite phenomenal. The next thing I'm going to discuss with you is Aurorae, also commonly referred to as the northern and southern lights, and I'm going to tell you from a physics point of view how they arise, how are Aurorae made. So these Van Allen magnetic bottles, they're leaky at their mirror parts, and charged particles therefore escape, mostly from the inner belt, but sometimes we see it from the outer belt. And these charged particles, they tend to interact with atoms in the upper atmosphere, and when these charged particles strike nitrogen and oxygen molecules specifically, they cause the electrons in those atoms to be excited to higher energy levels, and when these electrons return to their original energy levels, they emit light, oxygen emitting green and red light, whereas nitrogen emits violet light, and therefore they produce aurora borealis and aurora australis, or as they are more commonly known, the northern and southern lights.